question, we're told that a car of mass 1,500 kilograms is towing a trailer which has a mass of 500 kilograms. It's towing with a light, rigid, horizontal tow bar. The car is experiencing a constant air resistance of 300 newtons, while the corresponding constant air resistance, which is acting on the trailer, is 100 newtons. The car and the trailer are modelled as particles. Given that the tension in the tow bar is 200 newtons, calculate the acceleration of the system. Okay, a lot of information there. The very first step is to model this in a good diagram. So here's my two particles, the car and the trailer. We know that the car has a mass of 1,500 kilograms, while the trailer is 500 kilograms. We'll model the direction of movement, as in moving from left to right. Here's the tow bar that connects them. And now let's think of the forces that we need to add. So we're told that the resistive force on the car is 300 newtons. Resistive force on the trailer is 100 newtons. We're also told that the tension in the tow bar is 200 newtons. So I can add all of this to the diagram. The only force we don't know is the driving force. We do know that this system is in motion. We do know that the car is moving. Otherwise, there wouldn't be any resistance, there wouldn't be any tension. So we know that we're in motion. We have an unknown driving force. We've been asked to find the acceleration of the system. So we're going to use our motion equation, Newton's second law, F equals ma. And we'll focus on the trailer because there aren't any unknown forces on the trailer. 200 minus 100 is the resultant force, equals mass times acceleration. If we solve for acceleration, we get 1 over 5 or 0.2. So there we go, the acceleration of the system, 0.2 meters per second squared. Part 2 of Part A asks us to find the driving force, this unknown force, that force that we're calling D. I'm going to once again use the motion equation, Newton's second law, and focus on the car. So the resultant force would be the driving force, subtract 300, subtract 200. And that equals the mass of the car multiplied by the acceleration we just found. D is the only unknown, so we're really just rearranging to solve for D. In this case, the driving force is 800 newtons. The question continues and tells us that later in the journey, the car's driving force is removed and the car's brakes are applied. Now these brakes provide a constant braking force of 400 newtons, and that applies to the car only. The air resistance on the car and the trailer are unchanged, and we're asked to determine two things: the deceleration of the system and the thrust in the tow bar. So I'm actually going to redraw this diagram. Lots of things remain the same. We have the same resistances. There's nothing that would have made the masses change, and we're still connected by this tow bar. I've removed the driving force because we've been told there is no longer any driving force. What we have instead is a constant braking force of 400, and that braking force is in the negative direction. It's against the direction of motion. So we're braking with 400 newtons. The tension that we used to have was a pulling force, and the car was pulling the trailer along. Well, we no longer have tension because the car is braking and is actually trying to slow down. The trailer has nothing slowing it down. The trailer, however, has inertia and is going to continue to try to move forwards, which means that the trailer is pushing into the car, which means the car is pushing back into the trailer. So we have thrust in the tow bar. So this is what the diagram looks like. We're going to go again with F equals ma. This is Newton's second law of motion. We'll start with the trailer. The resultant force on the trailer, all of the forces are negative. Negative T minus 100 equals 500A. We have an unknown T and an unknown A. Let's move our attention over to the car. We have one positive force and two negative forces. negative 700, that's the air resistance and the braking force, plus T equals 1500A. We're in that familiar situation where we have a simultaneous equation that we can actually solve quite easily. We just need to add together the left-hand sides, add together the right-hand sides. That will eliminate T. I had one negative T and a positive T because the two places where we modelled thrust, the thrust was moving in two opposite directions. Let's add them together. That gives us negative 800 equal to 2000A. And we can easily solve for A. A is negative 800 over 2000. Simplifies so nicely down to negative 8 over 20. As a decimal, 0.4. Negative 0.4 meters per second squared. This makes sense. We're decelerating. We've applied the brakes. Everything in this system is slowing down. So the acceleration would be and should be negative. So a little bit of a sense check that you can do there. The last part asks us to find the thrust. Now, if you use this technique the way I've always asked you to, we are also going to solve for T, just by substituting our value for A. Let's substitute into the first equation. Negative T minus 100 equals 500 multiplied by negative 0.4. Expanding, simplifying, rearranging leads us all down to T equals 100. The thrust is 100 newtons.